Hello students, in this part of electric potential, we will first discuss about electric potential energy. As we know, a repulsive force acts between similar charges and a attractive force acts between dissimilar charges. If two similar charges are moved towards each other or two dissimilar charges are moved far apart from each other, then some work has to be done, and this work has to be done against the electrostatic force working between the charges. This work is stored in the form of potential energy of the system of the charges. When the charges are placed at infinite distance, then there is no force acting between them, so the potential energy is considered to be zero. So if any charge is placed at infinite, its potential energy will be zero. So the electric potential energy of a system of fixed charges is equal to the amount of work done by some external agent in forming the system by bringing each of them from infinity to that point. I will first calculate the electric potential energy due to a system of charges having only two charges. So here there are two charges Q1 and Q2 placed at distance small r apart, and we want to calculate the potential energy of the system. So initially I will consider that these charges are situated at infinity and they are brought from infinity to the position A and B small r apart from each other. So some work has to be done in bringing these charges in this position, and that work will be stored in the system of these charges in the form of potential energy. Here the potential energy of this system will be equal to the work done in bringing Q1 from infinity to point A plus work done in bringing Q2 from infinity to point B. So potential energy U is equal to W1 plus W2. Now Q1 is placed at infinity, and when Q1 is brought to position A, then there is no electric field, and hence the work done in bringing Q1 from infinity to this point A will be 0. So W1 will be 0. Now the work done in bringing Q2 from infinity to point B, this will be W2 is equal to Q2 into VB minus V infinity, because this charge will move in the electric field of charge Q1. So work done will be obtained as Q2 VB minus V infinity will be 0. So it will be Q2 into VB. But the electric potential due to charge Q1 at point B is given as VB is equal to 1 upon 4 pi epsilon 0 Q1 by small r. We will substitute this value of VB here. So we get W2 is equal to Q2 into 1 upon 4 pi epsilon 0 Q1 by r. So W2 is equal to 1 upon 4 pi epsilon 0 Q1 Q2 by small r. This is the work done in bringing this charge Q2 from infinity to point B in the electric field of charge Q1. So the total work done in forming this system, that is the potential energy of this system, U is equal to W1 plus W2, W1 is 0 plus W2. So you get potential energy 1 upon 4 pi epsilon 0 Q1 Q2 by small r. You have to note few things here. Number one, potential energy is a scalar quantity, so the value of charges should be placed along with their sign when we solve numerical problems. Number two, if both the charges are of same sign, means Q1 Q2 is greater than 0, in that case potential energy will be positive. Since similar charges repel each other, so in bringing them closer, some work has to be done against the repulsive force. So the electric potential energy of the system will increase. However, in separating them, work is done by the system itself, so its potential energy decreases. Next is, if both the charges are of opposite nature, in that case Q1, Q2 is less than 0, potential energy will be negative, since opposite charges attract each other. So in bringing them closer, work is done by the system itself, so its potential energy decreases. However, in separating them, its potential energy increases. Conclusion is that higher the negative value of potential energy of the system, greater will be its stability. So one thing is clear, that potential energy of a system of charges decides the stability of the system. Next is potential energy of the electric dipole in uniform electric field. What is uniform electric field, and from where we can obtain this uniform electric field? Let us look here. If this is a positive plate, means plate which is positively charged, and this is a plate which is negatively charged, then between these plates you can obtain a uniform electric field. Now the electric dipole is placed inside this electric field in this way, and we want to obtain the electrical potential energy of this dipole in this electric field. So first look here, the work done in rotating an electric dipole from the position of 0 energy to some specific position inside the electric field is equal to the potential energy of the dipole in that position. So the electric potential energy of the dipole in this position is obtained from the work done in rotating this dipole from the position of 0 potential energy to this specific position. Now the potential energy of dipole is 0 when it is placed perpendicular to the electric field, means when the dipole is placed in this way in the electric field, then its potential energy will be 0. We will rotate the dipole from this position to this position and obtain the work done, which will be equal to the potential energy of the dipole in this position. So as we know from our previous chapters, the torque acting on the dipole when it is kept in the state of theta deflection inside the electric field is tau is equal to Pe sin theta. Now work done in rotating the dipole by a small angle d theta from this position is, we will rotate the dipole by a small angle d theta from this position, then work done will be dw is equal to tau d theta. Therefore work done in rotating the dipole by a angle theta from the position of 0 energy, that is the potential energy of the dipole, will be u is equal to w integral dw, and from 90 to theta. Suppose that the dipole is rotated from this position to this position by angle theta, like this. Here this is angle theta. So we get integral 90 to theta tau d theta. We will substitute the value of tau. This will be Pe sin theta. P is constant taken out of the integration. It will integral 90 to theta sin theta d theta. Integration of sin theta with respect to d theta will be minus cos theta. Minus is taken outside, so we will get minus Pe, upper limit minus lower limit. This will be cos theta minus cos 90. So you will get u is equal to minus Pe cos theta. First case, we will see some special cases here. Potential energy in the state of stable equilibrium. If you leave the dipole here in the electric field, it will rotate like this and align itself along the direction of electric field with its positive charge facing towards the negative plate. This is the stable position or stable equilibrium of the dipole inside the electric field. In this condition, theta is 0 degree. So you will get u is equal to minus Pe cos 0, u is equal to minus Pe. Next is when the electric dipole is perpendicular to the electric field, means electric dipole is placed like this at an angle of 90 degree from the electric field. In this case theta is 90 degree, so you get minus Pe cos 90. Here the potential energy will be 0. Next is when the dipole is in the state of 180 degree deflection, means its positive charge is facing towards the positive plate and the negative charge facing towards the negative plate. This is 180 degree deflection. Here u is equal to minus Pe cos 180 degree, so u is equal to plus Pe. In this case you can see potential energy is positive, so this is unstable equilibrium. Here the potential energy is negative and this is the state of stable equilibrium.